You'd have to come move in front over here. Sorry. Which one, Corey? Number 7. Okay. Yeah, it's still a good thing to be aware of. All right. So natural numbers, whole numbers, integers, rational numbers. So last quarter, we went over natural numbers, whole numbers, and integers. This quarter, chapter 6, is all about the rational numbers. Okay, rational numbers is just a fraction. So how do they fit in a Venn diagram? Okay, so let's just list some items in each set. So natural numbers, oops. What are the natural numbers? Yes, they're counting numbers, right? 1, 2, 3, and forever, that way. And then the whole numbers, how are they different? Yeah. So what numbers are the whole numbers? The counting numbers, but there's more. Nope, those are integers. Negatives are integers. Yeah, so the whole numbers have a 0. So the whole numbers are the natural numbers plus 0. Integers are where we needed opposites of whole numbers. So we have 0, 1, 2, 3 in one direction, and we have -1, -2, and so on in the other direction. So those are the integers. Fractions are a bit more complicated, are the rational numbers. If you look in the book in section 6.1, they say that definition of a rational number is something that looks like A over B, where A and B are integers. And there's one other catch. B can't be 0, otherwise we don't have a number. Okay, so just for example, those are numbers like 1/2, -3/4, 17/5, and so on. Pretty much any fraction, positive, negative, even numbers like 2/1, right? So would you agree then that every integer is a rational number? Because I can always write it the integer over 1. So every integer is a rational number. So thinking about a Venn diagram, rational numbers at the moment is the biggest set we have. And the integers live inside there. What about the whole numbers? Are the whole numbers part of the integers, for example? Yeah. So the whole numbers live inside the integer set. Let's pick a new color. And then the natural numbers sit inside the whole numbers. So that's a similar picture to the one I put in the key. Yeah, so you just kind of list out what does it mean to be an integer, what does it mean to be a whole number, what does it mean to be a natural number, and then as you compare them, you see how they fit together. And so remember, we started the course with just looking at natural numbers, and then we added 0. Then we decided we needed negative numbers because we needed opposites for like subtraction. Division leads us to need the rational numbers. In the next chapter, we're going to pick up another set of numbers that we need to work with too. we're not quite ready for that. That's that one. All right, what else did you want to take a look at? Okay. Yeah, so if compared to what I did in class, let's take, how about 1/12 and 1/20th, for example. What's the standard algorithm called for adding fractions? Yeah, it's the LCD algorithm is what we usually use. So quick review of that. LCD algorithm says to first find the lowest common multiple of the two numbers, 12 and 20. And a couple of different ways we could do that. I like to just factor them both and use that. So off to the side here, I would need to know 12 is 2 times 6, and 6 is 2 times 3. And then 20 is what, 2 times 10, and 10 is 2 times 5. So 12 says, well, if someone's going to be a multiple of me, it needs to have a 2 in it, another 2 in it, and a 3 in it. 5 says, yeah, I like the 2 2s. I don't care about the 3, but I need a 5. Other way to think about that, 2 squared times 3 times 5. Based on the prime factorizations here, 12 is 2 squared times 3. And 20 is 2 squared times 5. And the rule we came up with was you need the lowest power of all common, let's say, wait, no, sorry, you want the highest power of all primes present, was how we came up with the LCM. So I got the highest power of 2, I got the highest power of 3, and I got the highest power of 5, all living in here. So let's see, what's that? 4 times 3 is 12, 12 times 5 is 60. So 60 is what we call the LCD, lowest common denominator. So that's like the first step in finding the finishing the LCD algorithm. Second step is you have to divide each denominator into that. So I have to take 60 divided by 12, which tells me I need a multiple of 5 for the first fraction. And I have to take 60 divided by 20, which tells me the second fraction is missing a factor of 3. So based on that, I can say I take the 1/12 and I multiply top and bottom by 5. And I take the 1/20th and I multiply top and bottom by 3. So now I'm adding 5/60ths to 3/60ths. And so I think the answer is 8/60ths. Yeah, so now the thing about the LCD is it gives us the lowest possible denominator I can get away with. However, sometimes the answer still reduces. So Corey mentioned that 4 goes in the top and bottom. And so that could be reduced down to 2/15. Kind of an interesting fact about when it does reduce. What's the GCD of 12 and 20? What's the biggest divisor they have in common? Yeah, it's, well, not just 2, right? If you look up here at their factorizations, they both have 2 squared or 4 in common. Now, it's not always going to be true that you get to reduce by the GCD, but you're going to be, you can reduce by the GCD or something that goes into it. So if I know 4 is the GCD, that means if the sum reduces, it's going to be reducing by a 4 or a 2. So there's that relationship between the LCM and the GCD. So that's one algorithm. Another algorithm, if you look in the book says if you have a fraction a over b plus another fraction c over d, and as long as the denominator is on 0, the book just called this the definition of adding fractions. They say the sum has to be AD plus BC over BD. So the question is, how the heck did they get that? Well, what they did is they just said, well, a quick way to get a denominator is just to multiply the two denominators together. And that's where BD comes from. And then they cross multiply the D by the A and the B by the C. So if I take an approach on this that's similar to the LCM algorithm, I just say, I don't even care about the lowest common denominator. I just say, I'm going to make my denominator B times D. That's going to be my new denominator because it's right there in front of me. I don't have to think any more than that. Well, if I multiply D in this fraction right here in the bottom, I got to do the same thing in the top. So I'm going to have to do A times D in the top. If I multiply this denominator by B, then I better do the same thing in the top. Now I have a common denominator, so that's my new denominator, BD, and the sum has to be the two numerators, AD plus BC. So if you look at it the way I have right here, I call this the arrow algorithm. Using that process of arrows, the book, if you memorize that formula, just calls this the definition of fraction addition, which is an algorithm. Follow that formula. Okay. So you could either say, hey, definition is this, that's my algorithm, or you could use the arrow algorithm. So if I'm going to demonstrate the arrow algorithm on, let's try it, 1/12 and what was it, 1/20th? Then I would say my denominator is 12 times 20, which I think is 240. And then I cross multiply denominator to numerator, and that gives me 20 plus 12. So my sum has to be 20 plus 12, which is what, 32? Over 240. And then reduce. Okay, let's see, 2 goes in the top and bottom, right? So I could say this is 16 over 120. They're both still even, so I could take 2 in again. So that would be what, 8 over 60? And I keep trying until I can't anymore. What do you think? 2 goes again, 4 over 30. And then finally we get the same thing we got before, which was 2 over 15. Now I had to reduce 1 extra time right there. Actually 2 extra times, 1, 2. Here the LCM took us right to that one right there. So it comes down to, well, is it better to just grab a common denominator by multiplying the denominators and then reducing, or going through the process of calculating the lowest common multiple, using that to calculate multiples to rewrite each fraction, and then finally you get to add them. So this has 2 steps in the beginning the other one doesn't have, but this one had a couple extra reductions at the end. And some people argue, hey, reducing is way easier than finding a lowest common multiple. That's hard. So some people say, let's just use the LCM algorithm. Now, you're really going to end up seeing both in your textbooks in school and in the programs you go into. You could argue that in elementary school, you really only need the arrow algorithm and then teach them how to reduce. But if they ever go into algebra, the LCD algorithm is super important in algebra. So it's a tough one there. And let's see, do I know any other fraction addition algorithms? I think that's all I know right now off the top of my head. All right, what else do you want to do?
I don't understand on this one where it says illustrate and explain 2/3 over 3 over 2. But I don't understand how you can have 3 of 2. Like, I know that on the thing you put it like that.
2/3 plus 3/2, number 2.
And
Okay.
my answer did not.
All right, so illustrate and explain 2/3 plus 3/2. So, new page, 2/3 plus 3/2. So first I have to decide, just remind myself, what does addition mean? So addition means combine. Yeah. Add means combine. And then what is a fraction? A part of a whole is what we usually do. So I have to draw each of these as part of a whole. And you could use pies if you want. I prefer cakes that are square. So I have to draw 2/3. So there's thirds, and then I need to pick a couple to shade. So maybe I'll shade this one and that one. So there's my 2/3. Then I got to draw my 3/2. It's not quite the same size. Oh, well, close enough. So when I cut it in half, I have 2 halves, right? So I need to draw another hole to show the 3rd half. Oops, and I meant to, because what's 3/2? Because isn't 3/2 if we take 2 into 3, right? It's 1 1/2. If I think about it as a mixed number, yeah. So let me redraw that, hang on. Oops, oh man, I didn't mean to redo all that. Oh well. Okay, so I'm gonna cut it in half the other way because then it's easier to draw. But in order to show 3/2, I have to draw another hole. Oops, and so now I can say there's 1, 2, and 3/2. Yeah. So here, right, so here, let me switch. You're live. Good to see you. So here's my 1 1/2, right? Which is also 1, 2, 3 halves of a whole. Okay. Now I need to put them together. Now, add, there's something we left off what add means. Add means combine and count. And it's not really helpful to say I have 1, 2, 3, 4, 5 pieces because they're different sizes. So now I have to cut each cake like the other. Where'd you drive in from, Brianna? Are you in town here, or how are the roads? Not too bad, okay. Yeah, so this cake needs to be cut in half. This cake needs to be cut in thirds. So now the way I've rewrote it here, I have 1, 2, 3, 4 pieces out of 6 in that one. Here I have 6, 7, 8, 9 pieces, and each hole has 6 in it. Altogether, how many pieces do I have shaded? Well, I've got 4 and 9, which gives me 13 altogether. And as far as a whole goes, there are 6 equal parts of a whole. So the answer's got to be 13/6. If you want to write it as a mixed number, then you'd have to regroup them. So I'll do that on another page. So when I put them together, Well, I had, for example, completely filled up one hole. I had another one that had, oops, extra line, sorry about that. That had 1, 2, 3, 4 pieces. And then there was another one that had what, 3 chunks in it? Or was it 4 chunks? 1, 2, 3 chunks. 1, 2, I need to draw another cake to get that fourth one in. So shading them like they were before, we had a cake that had 6 pieces filling it up. We had another one that had 4 in it. And another one that had 1, 2, 3 more. And so altogether, I need 3 holes to demonstrate the answer. Right? Let's see, 6 and 6 is what? 12 plus 1 is 13. So this still shows I have 13, 6, but now I can see the answer is also what? 2 and 1/6. Right? 1, 2, and 1/6. So here's my 1½ right here, right? And here's my 2/3. When I put it all together, I can either say the answer is 13 pieces out of 6 in a hole, 13, 6, or if I start taking these pieces and I stick them in there, I can show the answer is 2 and 1/6. So depending how you look at it, we showed that 2/3 plus 3/2 is either 13, 6 or 2 and 1/6. So to illustrate and explain, here's my illustration. My explanation is add means combine and count, fraction is equal part of a whole, and I have to cut each cake like the other to combine and count. So you're gonna have to write a few sentences to go along with your pictures explaining what's going on. We did a similar thing with the pattern blocks. And we did some square cakes like this in class too a couple weeks ago. Do you want to do another one of those or do you have another question? Okay, what is it? Yep. Number 4, yeah. So we want to take 1½ times 2 3/4. Okay. So here we're multiplying, let's see, what was it? 1½ by 2 3/4. Okay. So to do that, I have to know a couple of things. What is a fraction and then what is multiplication? So first, I stated up front, let multiplication be an area. So multiplication is an area. I consider area to be a base by a height. And so I have to pick one of these numbers to be the base and the other one to be the height. Usually I pick the bigger number to be the base, but it doesn't matter which way you go. So I'm going to say the 1½ is my base, and the 2 3/4 is my height. Now, other thing to consider is what a fraction means. Fraction is what? Well, usually we consider to be part of a whole. All right, so I have to have the setup to explain what's going on. What does a whole mean with area? What would one whole area be? One times 1 is 1, right? So a whole area is a square that is 1 by 1. That's one whole, right? Because I have the area model. The only way to get one whole is 1 times 1. Well, there's other ways to get it, but that's the easiest way. Okay, so I know what a whole is now. I know what multiplication means, so now I have to draw that out. So it's an area. I'm claiming my base is 1.5, so I'm going to draw a baseline. I'm going to measure 1 over. So if that's 1, 2 would be about here, and 1.5 would be about right there, according to the number line model, right? And then I have to go up for my height. So if that's 1, let's see, that's about an eraser. So there's 1. Uh-oh, I'm running out of room. There's 2. 3 would be up by my t. I need to cut that into halves and then quarters. So if this is 1, that's 2. That line right there would be 2 3/4. And I'm going to see if I can move some of this out of my way. I think I just need a new screen. So I'll get a new screen in a second. But I need to figure out now what this region right here is. If this is a whole, how much lives in there? Big question mark. So new page, redraw that. So there's 1, 2, 3, 2.5, 2 3/4. 1, 2, 1.5. I need a new color. So I'm just going to grid this out as a 3 by 2 grid for now. I want to isolate the part that is 1.5 by 2 3/4. So this is my area right here. So to finish this, what I would say is, well, we know that, oops, wrong type of thing. We know that this is 1 unit high that way, that's 2 units high that way. We know this would be 1 unit of width. So right away I can say, here's one hole right there, isn't it? Isn't that 1 by 1? And this region right here is 1 by 1. This one's not quite big enough yet, right? So I've got some more work to do. How did we figure out when we were adding fractions? When we were adding fractions, we cut each one like the other. So I just have to do some more cutting. So what I'm going to do is I'm going to say cut this in half here too. So just do everything in halves. And in this way, I'm just going to cut everything in quarters. Okay, so let's see. If I come across this way, I have 1, 2, 3 columns, right? I'll do this in 2 different ways. If I come this way here, I have 4 and 4 is 8, 9, 10, 11 rows. So my yellow shaded region has 33 little pieces in it right now. With the way I've cut this, how many pieces are in one hole? Well, a hole is half by quarters. So if it's 2 that way and 4 that way, how many little pieces are in a hole? 8. Yeah, so altogether, I must have here 33/8 as my answer. Right, because isn't this 3 halves wide? And isn't this 11 quarters tall? 11 times 3 means there are 33 little rectangles in there. Each rectangle is 1/8 of a hole. Okay. Other way to look at it, now that I have the 8s determined, I know that's one whole. Oops, I want a highlighter. I know this is one whole, right? And then I have to start looking for 8 pieces at a time, okay? Because aren't 8 pieces a whole here? Okay, 1, 2, 3, 4, 5, 6, 7, 8. So here is another whole. 1, 2, 3, 4, 5, 6, 7, 8. So here is yet another whole. So how many holes do I have so far? 1, 2, 3, 4 holes. So we're also thinking that the answer, blue pen, yep, is 4. And how much is left over? Just one piece? 1/8, yeah, so 4 1/8 is another way to look at it. So you got to draw the area, and then you got to use your denominators to kind of break it up and figure out what a whole means. And then you can either do the improper fraction version by just counting all the little rectangles and stating how many are in a whole, or you can start looking for groups of 8, and then you can write it as a mixed number. Should we do another one of those, or do we have another question? Mm-hmm. So one thing we went over in class a while ago is, so think about this for a second. If I draw a number line, suppose I say that's 0 and that's 1 right there. How many fractions live in between there? There's an infinitely many fractions in there, right? You pick any number you want, that can be the denominator, and then you throw a numerator on it that's smaller than it, and then you have something in there. Now, I said to use what, 9/10? So maybe 9/10 lives about there. Now I could, oops, 9/10, sorry. I could zoom in on that, and if I zoom in, I could say, well, here is 9/10, and here is 1. How many fractions do you think live in between there and there? Turns out there's infinitely many. Okay, so that's supposed to be a 10, by the way. That didn't come out very good. Eraser. So now we have to find some way to get them. So we played around with this one day in class, and people came up with a lot of different ways. Well, I could find the number in the middle, couldn't I? What's the number in between two numbers called? Average. Average? Well, it's halfway in between, right? Yeah. So the number in the middle is going to be this number plus that number over 2. So I could take 9/10, add it to 1, and then divide by 2. That's going to give me the number in the middle. Well, that would be what? 9/10 and 10/10, which is 19/10. Cut that in half, and 19/20 would be the number exactly in the middle. Now, can't you find the number in between 19/20 and 9/10? Yeah, just add those two up, divide by 2. You could do that all day long. So you could find that number and 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 that number by just keep cutting things in half. You can make anything up you want. So here's another way to do it. Yeah. So here's 9/10. Here's 1 whole. I could say this is 90/100ths, in which case this right here would be 100/100ths. So give me something in between. 91/100ths, yeah, right. And you could have said that's 900/1000ths and 1000/1000ths, and you give me a ton of numbers in between there, and we could do this all day long, forever and ever and ever. Yeah, so it doesn't matter how close the fractions seem to be. There's always infinitely many in between. You just got to find some way to find them. Easiest way is what we're doing right now. Just do something like multiply top and bottom by 1,000, and you just expanded it immensely. That is tedious, but you can do it. Yeah.
I was like so wrong. I got the 19/20.
Mm-hmm. Oh yeah, so somehow you ended up going, you jumped to the other side somewhere. My guess is you probably, I'd have to look at the end. Yeah, so you get a little arithmetic error on one of them that threw you outside, and then it started to go bad. But yeah, but theoretically, you should be able to keep cutting them in half. So I could find the average value of 19/20 and 9/10, and that'll give me whatever that number is right there. Well, 2/3, I mean, think about it. If this is 1/3, 2/3 would be here, which is, so 2/3 wouldn't be in between. You could make random guesses, but then you'd have to check to see if it fell in there. So that wouldn't be an efficient strategy. Yeah, so you want something that's bigger than 9/10 but smaller than 1. That's why either finding the average is a good strategy, but a lot of work, or just rewriting them with a bigger denominator. Yeah, like in my notes, I decided to make 60 the denominator, and then I let 100 be the denominator. You just have to make the denominator big enough. Here's a trick somebody did before that I thought was cute. 9/10 and 1, they said, well, shouldn't 9.1 be just a little bigger than 9/10? Now the problem is 9.1 isn't the whole number. So the trick there is to say, well, if you multiply top and bottom by 10, that would be 91/100. Okay, so he just fiddled with what he knew about decimals and then found another number, and then you could keep doing that too. Yeah, as long as over here we're smaller than 10/10, or whatever denominator we go for. Yeah. Okay, Corey, you said you had questions, but I think you only asked one so far. Did you have? Oh, you did ask them both. Okay. Yeah. All right.
So with the 2/5 on the test into 4 different factor representations,
Yes.
you just want like the cake is 2/5 and then like dots, color 2.
Yeah, so let me bring up my answers here. Number 1 on the practice test. Yeah. So here, the different ways we looked at fractions, let me blow that up a little more for our studio audience. Hopefully this is gonna go one more. So here, one way is part of a whole region is my first example for 3/4. And then we could have part of a whole group. And so that's a slightly different version of the picture. 3/4 could be a division problem. You have 3 things, you have to break it into 4 parts. And so you have to cut it in such a way that they're equal parts. However, it could be a ratio, which we talked about in the beginning of the quarter and in the last section. In this case, I have a group of 7 people. 3 of them are male, 4 of them are female. So there's a ratio of 3 to 4 for boys to girls. That's totally not a part of a whole. And the other thing we talked about is a position on a number line. The book had a 6th way of looking at it. Does anyone remember what the book's 6th way was? It was the idea of probability, that's a different kind of fraction. But my thought is that probability really is part of a whole or a ratio, so I didn't single it out as being different. What do you got?
I just did a cube and then put in 4 on the cube.
Mm-hmm.
Would that work?
Yeah.
Okay.
Yeah.
Because when I saw that, I was like, oh.
Yeah, and on the take-home test, I asked you to give me more than one different way to represent it. So that's like here. So here I give 5 different ways to talk about what 3/4 means. Yeah. And so another place you could look for more examples is, I think it's on page 1 of 6.1. They have similar pictures with what different ways we interpret fractions in reality. Yep. Other questions? Number 11 on the 6 post-test. Okay, so number 11 says, with the exception of 2/3, yeah, so this is interesting. When the Egyptians did fractions, most fractions, they only had 1 as a numerator. So they didn't have like 2/5 or 3/5 or 7/10. It had to be 1 over something. And so here they're giving us a trick for trying to turn things into 1 over something. And so they give some examples here. Find at least 2 different unit fraction representations for 1/3 and 1/7. Yeah, so we can play around with that a little bit. So, oops, wrong way. All right, and then I want to screenshot that. So let's see, 1/3. So one way to play around with it is just to draw 1/3 and see what we can come up with. So drawing a third, I might do it like this. And here is 1/3. All right, and then if 1/3 is going to be equal to the sum of 2 other fractions, well, they're going to have to be smaller than 1/3, right? So that means we're going to have to break this up into smaller pieces. So I could maybe try cutting it in half and see if that helps. So if I cut it in half, I've just represented it as what, 2/6 here? So couldn't I then take this guy, which is 1/6, and then that guy, which is 1/6? And there could be other ways, but sometimes, you might try something and it might not work. So for example, I might have tried starting with 1/3. And maybe I tried cutting it into ninths, right? Because it's a 3x3 grid. So I could take just that guy right there. That would be 1/3, right? But then this guy right here is 2/9, and the Egyptians wouldn't understand 2/9, so that wouldn't work. So then I'd have to say, okay, can I break 2/9 into ones? Well, oops, sorry, this is supposed to be 1/9. Now here they said, hey, at least 2 different fractions. Well, couldn't I just say 1/9 and 1/9 and 1/9? Because they said at least 2. So I could say it's 1/9 and 1/9 and 1/9. Oops. This is on the post test, yeah. The Egyptian fractions.
The only thing I missed on that was rewriting this.
As an addition. This problem right here or a different problem? This one right here? Okay. Yeah. Mm-hmm. Yes. Okay. Yeah. Let's take a look at B and C next. So they say to compute 1 over n minus 1 over n plus 1. Let's see what that looks like. So that'd be 1 over n minus 1 over n plus 1. I think I copied that right. All right, so if I want to combine those, I got to have a common denominator. And the easiest thing to do is use our arrow algorithm here. And so the common denominator here is going to be the product of the 2 denominators, n times n plus 1. If that's the case, then the first fraction is missing an n plus 1 top and bottom. So the first fraction I could say is n plus 1 over n plus 1 times n. What's the second one missing from the common denominator? An n, so I'd have to multiply that one top and bottom by n. So that gives me n over n plus 1 times n. So now I have a common denominator. I can just combine the numerators. So the answer's got to be n plus 1 times n. And in the numerator, I have n plus 1 minus n. Does the numerator clean up a little bit? Yeah, I've got an n minus an n, that cancels. So this must add up to 1 over n times n plus 1 in the denominator. Okay, so let me just rewrite that underneath here. So for part B, we've determined that 1 over n minus 1 over n plus 1 is the same thing as 1 over n times n plus 1. Now, right now, it's a subtraction problem, right? What could we do to rewrite this as an addition problem? Add it to the other side, you mean? Yeah, add it. Yeah, so we know some algebras, we can just add it to the other side. Other way to think about it is we know fact families. If A minus B equals C, then that means C plus B has to be A. Okay, so we can bounce around fact families. So that would mean different color. Let's try blue. 1 over n stays over here, and on the other side, I get 1 over n times n plus 1 plus 1 over n. Plus 1. Oops, yes, thank you, sorry. So now I've rewritten it as the sum of two fractions. So for example, if n was something like 5, then this would say 1/5 is equal to, well, if n is 5, what's n plus 1 have to be? 6, right? The next one would be 6. 5 plus 1 is 6. So this would be 1 over 5 times 6, or 1/30. And then this is 1/6 here. So this formula says 1/5 has to be equal to 1/30 plus 1/6. Because 30 is 5 times 6. No. It's just an interesting, so the Egyptians discovered this in the way they dealt with fractions. They never wrote it algebraically, they just kind of had an intuitive understanding of it. Let's just double check that that's true with the 1/30 and 1/6. What's the lowest common denominator here? It'd be 30 because 6 goes into 30, right? So that's nice. So I would just multiply top and bottom by 5. So that means I have a denominator of 30 and my numerators are 1 and 5. 1 plus 5 is 6. Can I reduce 6/30? Yeah, 6 goes into 30 5 times, so this is 1/5. So the formula they stated is true.
So then you just leave it like that. I think what I did wrong was when I did it on the computer, I put the n, like I made the denominators the same.
Yeah, the denominators are different here, and we can just leave them that way. Yeah.
So I mean, like the one on the right was n times n plus 1 n.
Okay. So, and we could use this anywhere. Like, remember we were messing around with 1/3 earlier? So we could use this for the rewriting 1/3. The formula says this is going to be equal to 1 over 3 times 4 plus 1 over 4. Well, that would be what, 1/12 plus 1/4? So that would be another way to rewrite it. Double check to see if that's true picture-wise. If I start with 1/3, this formula here says to rewrite this as 12ths. Well, if I just cut this side into quarters, don't I have 12ths now? Okay, so here's 1/12, right? And this right here is 3/12, which reduces to what? Yeah, whoa, what did I do? Sorry about that. That was interesting. Yeah, 3/12, which is my 1/4. Yeah, so we can show it with a picture. And years ago, I remember reading more about how the Egyptians did fractions, but I can't remember all the details, how they went about doing it. They didn't do algebra, that's for sure. But they had this concept. And then what was the next one? They asked me to do it for 1/17. Yeah. And yeah, so we had done 1/7. Oh, we didn't do 1/7 yet, did we? Yeah, so we could use this trick for 1/7. And again, the formula says, given something like 1 over n, you can rewrite it as 1 over n times n plus 1, right? So a number times it's the next one, and 1 over n plus 1. So if we say n is 7, what's the first fraction on the other side then? It would be 1 over what? If n is 7, what's n plus 1? 8. 7 times 8 is 56 on a good day. Is that right? And then this would be just 1/8. We could do the same thing with 1/17. 1/17. Now this one I can't do in my head. That would be 1 over whatever 17 times 18 is. Somebody with a calculator help me out there. Plus 1/18. Anybody's got a calculator? All right. What is it? 306. Okay. So according to this, if we take 1 over 306 and add it to 1/18, we should get 1/17 back.
It's pretty much two numbers that divide to make a 7.
Mm-hmm. No. It's just an exercise in you getting better with fractions.
I have another question.
Okay, what's up?
So on the front side of it, I don't know why, but I think about how to do it. It says 8 minus 6, parentheses, 5 minus 2/3, parentheses, squared. The bottom one.
The bottom one. Okay, let's take a look at that one.
No, no, I don't.
Page. The last one on the first page.
Oh, on the back of that?
Yep. All right, so reminder, order of operations. First step is parentheses. Second step is exponents. Third step is multiplication or division as you view it left to right. Fourth step, addition or subtraction as you view it left to right. So here, I have to go inside the parentheses first and figure out what is 5 minus 2/3. So I would view that as 5 over 1 minus 2 over 3. And here I could just as easily use the arrow algorithm to pull it off, and we're not supposed to use a calculator. So denominator is 1 times 3. Numerators are 15 and 2, and I'm subtracting them. 15 minus 2 is what, 13? So now I have 8 minus 6 times parentheses 13/3 squared. So we just do it one step at a time. Okay, so order of operations. There's really not much to do inside the parentheses anymore. We've done it. So we move to the next step. Are there any exponents? Oh yeah, there's one right there. So what does it mean to square a number? Multiply by itself, right? So off to the side here, I need to figure out what is 13/3 times 13/3. My recollection is 13 times 13 is 169. Probably should write that down to double check. Let's see, that gives me what, 39 and 130. Yep, 169. Oops, that's supposed to be a 6. So on a test, write everything down. Don't do stuff in your head. So then I now have 8 minus 6 times 169 ninths. What's next? See, there's no more inside parentheses. There's no more exponents. Order of operations says do your multiplications or divisions next. Here is a combination of multiplication and division right there. Two ways to do it. You could just apply the multiplication algorithm, view that as 6 over 1 and multiply straight across the top and the bottom. Or you could remember multiplication is the only time you can reduce ahead of time. I have two different numerators here. Do these numerators have any factors in common with the denominators? Yeah, 3 goes into 6 and 9. So I could go over here and say, well, 3 goes into 6 twice, and 3 goes into 9 3 times. And that's the best I'm going to do because I know the 169 came from 13 times 13, and 13 thirds didn't reduce, so that's the best I got. So cleaning that up, where are we at? We've got 8 minus 2 times 169 is going to be what? Yeah, don't do it in your head, Gary. So 169 times 2, 9 times 2 is 18, 6 times 2 is 12, plus 1 is 13, 2 times 1 is 2, plus 1 is 3. I get this is now 8 minus 338 thirds. Last step is to do the subtraction, which I would just use the arrow algorithm again, viewing that as 8 over 1. My new denominator is 1 times 3. Numerators are 24 and 388, or 338, sorry. And I'm subtracting them. So 24 minus 338 is the opposite of 338 minus 24. 8 minus 4 is 4. 3 minus 2 is 1. So it looks like I get negative 314 over 3. Yeah. You will see this stuff for sure in 6th grade math. Probably not 5th grade unless you have some very advanced kids that you need to keep busy. You know, there was one I wanted to take a look at with you since nobody asked. Let's take a look at G, please. Yeah. 314, where'd it go? 314 thirds. Negative 314 thirds, thank you, yes. All right. All right, so G. So just a reminder, I'm just going to play with this a little bit. I'm not going to do it straightforward because I'm going to use it just to review some other ideas. Mixed number, when I look at something like 6 and a third, I put the word and in between them because that literally means 6 and 1/3. So what I have here is 6 and a third minus 2 and 3/4. So this is just a reminder that when you're playing around with mixed numbers, it's always best to write them as improper fractions. Otherwise, you got a lot of work to do. Because here, since I put the parentheses around it, I would have to distribute that negative sign to get it right? Because that's 2 and a third, I'm subtracting the whole thing. Both the 2 is being subtracted and the 3/4 is being subtracted. So algorithm for turning a mixed number into an improper is kind of a rotation. 6 times 3 is 18, plus 1 gives me 19 thirds, minus 2 times 4 is 8, plus 3 is 11/4. Once I have those, it's just like any other fraction problem. I can then apply the arrow algorithm. 6 times 3 is 18 plus 1, right? Because I need a common denominator for the 6 and the 1/3, and the common denominator would be 3. Yeah, 6 would be 18 thirds plus 1/3. So now I can say the common denominator, or a common denominator, is 12. My numerators, 4 times 19. Question? What's up, Danielle? Okay. 4 times 19, let's see, that's going to be 40 and 36, which is 76. 3 times 11 is 33. So the answer here should be 76 minus 33, which is 43 twelfths. Do I have to reduce it? Do I have to change it to a mixed number? Answer is no, it's fine like that. You could if you want. The alternative algorithm here would be to stack them. And this is one way the book presents it. So let's compare this algorithm. Can I take 1/3 minus 3/4, or is that a problem? But I can't, I need a common denominator first. Yeah, so 12ths would be the common denominator. So I would rewrite that as 4/12 and this one as 9/12. But I'm still trying to subtract. Can I take 9/12 away from 4/12? The answer is no. So what do I have to do? I have to borrow, okay? So if I borrow from the 6, that makes it a 5. What am I bringing over to the 4/12? 12/12. Yeah, so 12/12 and 4/12 gives me 16/12. Most people are going to do what instead of putting 12/12 there? They're going to do like 10, like we do with whole numbers. Yeah, they're just going to call it 14, right? But that's not right. So that's an added layer of complication. But now I can say 16/12 minus 9/12. Well, that's just 7/12. 5 minus 2 is 3. So then you get to break it down. Well, what's easier? Borrowing for a common denominator or writing it as improper fractions and then treating them just like you do any other fraction. So my theory is there's less room for error here than over here, but they're both good. You will see them both in your textbooks. There's just different ways to handle it. Some teachers like to have only one strategy and that's all they teach in their class. Most of the workbooks and textbooks you'll see will always offer multiple strategies. Some kids are going to freak out over it. Some kids are going to love it. And so you just got to take a look at each kid and figure out what to do. All right. Hang on one sec. This broadcast, I think I'm done with the review. Give me one sec.